Unit 5, Video Lecture 1, Bonds, Chemical Bonds. So what are they? Bonds are forces that hold groups of atoms together that allow them to act as or function as a single unit. There are different types. There is the ionic bond, which is a result of transferring electrons. And there are covalent bonds, which is a result of sharing. We'll talk more about covalent bonds later. So when we talk about bonding forces, this is what holds atoms together. They're made up of attractive and repulsive forces. If we remember, the atom is made up of protons, neutrons, and electrons. Since neutrons are neutrally or have no charge, they're not going to be involved in these attractive or repulsive forces. We have electron-electron forces which push atoms apart, because since electrons are both negative, it's going to repel one another. We have proton-proton forces. These are both positive, so they are going to push each other away. But what keeps them together is the electron-proton attractive forces. Now, in an ionic bond, if we recall from last chapter, metals form a cation and we form cations by losing electrons, thereby resulting in a positive charge. By contrast, nonmetals form anions by gaining electrons, having a negative charge. Now, these electrons that we're talking about gaining or losing are our valence electrons. That's what we're concerned about. That's what we're going to be concerned about. And these valence electrons are going to be the electrons that are in the outermost energy level. So if we look at some group 1 elements, or if we look at some alkali metals, okay, we see lithium's electron configuration is 1s1, 2s1. Sodium is 1s2, 2s2, 2p6, 3s1. Potassium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. And if we do the noble gas configuration for rubidium, we see krypton 5s1. If we look, our outermost energy levels all have one valence electron. So if we were to draw electron dot diagrams, we'd use a symbol for any of them. So like lithium with 1 dot, sodium with 1 dot, potassium with 1 dot, or rubidium with 1 dot. All of our alkali metals have 1 valence electron. If we look at some halogens, and we take a look at their electron configurations, see if we look at the outermost energy level, where for fluorine it would be the energy level 2, and chlorine would be energy level 3, we would see energy level 2 and energy level 3 here both have 7 valence electrons. Now when we get down to bromine, 4 is the highest energy level. Now that's made up of both the 4s and the 4p. Even though they're separated by the 3d, we still have 7 valence electrons. Just like we'll see in iodine, even though the 5th energy level is separated by the 4d, we still have the 5s2, the 5p5, still having 7 valence electrons. So if we were to do electron dot diagrams, we would take any of our halogens and draw 7 dots around them. Now, it's fairly easy to predict valence electrons because, like we just saw, all of our alkali metals will have 1 valence electron. And what we just saw was all of our halogens will all have 7 valence electrons. Group 2, our alkaline earth metals, will have 2 valence electrons. If you notice the group number, so group number 2 will have 2 valence electrons. Group 3 will have 3 valence electrons. Group 4 will have 4. Group 5 will have 5. 6 will have 6. 7 will have 7. And group 8A will have 8. So now remember, these are for our representative groups. This does not hold true for our transition metals. So let's create some ionic bonds using Lewis dot structures. So if we look, sodium has 1 valence electron. Chlorine, we know, has 7. So sodium, a metal, will want to lose its 1 valence electron, resulting in a positive charge. Chlorine, the nonmetal, will want to gain an electron, resulting in a negative charge. So the 1 valence electron that is given up by sodium will be accepted by chlorine. This will create sodium with a positive charge and chlorine with a negative charge. Remember, in ionic bonds, electrons are transferred, and it's the electromagnetic forces that holds this compound together. The formation of an ionic bond is always exothermic, meaning that energy is going to be released. Now, when you have a bunch of these sodium chloride formula units coming together, they make some of the most beautiful things in nature. These sodium chloride crystals are all ionic compounds form solids at room temperature. They organize into this crystal of alternating positive and negative ions. This would be one molecule, this would be one formula unit of sodium chloride. Here would be another, here would be another. And we can see these different sodium chloride molecules are forming together. Now, some characteristics of ionic bonds. There's always going to be a cation and an anion. So there's always going to be a metal and a nonmetal. They have very high melting points. They're very high melting points because they're very stable. So the stability of this leads to high melting points. Ionic bonds are very brittle, and they dissolve in water or other polar solutions. When they're dissolved in water, they conduct electricity. When they're solid, they don't. But if we liquefy them, they do. And this is referring back to that conducting of electricity. Ions, like we said before, are made up of cations, which is the positive ions. These are examples of this is like we saw earlier with lithium or sodium in our sodium chloride. Examples of this would be like sodium with that +1 charge. Other examples would be like magnesium with a +2 charge, or this ammonium ion. It's a cation because of these positive charges. Anions are the negative ions, so like chlorine or sulfate. Ionic compounds form when atoms or groups of atoms have different numbers of positive and negative charges. When we talk about anions and cations, one of our first type is monoatomic. Okay, the prefix mono involves only one atom. We have the metals, which recall are the positive ions, and the anions, which are the negative ions. When we're naming these, our metals will always retain their name. So if we talk about the Na plus ion, that's just simply the sodium ion. If we talk about Ca positive 2, that's just simply the calcium ion. So they retain their names. The anion is going to use the shortened name or the root of the name followed by "ide." So when we talk about chlorine, we're going to use the chlor, and chlorine will become a chloride ion. If we're talking about nitrogen, we're going to keep the NiTr, and nitrogen would become, so these are both ions. Now, sometimes when we're talking about cations, we can have a cation that can form more than one ion. In this case, we're going to use Roman numerals to indicate the charge. So we'd use parentheses and the Roman numeral 3 to indicate a +3 ion, and Roman numeral 2 with a +2 ion. So what this would look like is if we were to talk about an aluminum ion, it would just be Al +3, but now Sn +4. Tin can form multiple ions. So we use Sn for tin, and the fact that it's +4 means that we use the Roman numeral 4. Best place to see some of these that form multiple ions would be mostly transition metals. And if you want a complete list of transition metals, I would refer to the back of your periodic table. Now, polyatomic cations and anions. Okay. Poly means many. So this involves more than one. More than one ion. They're bonded covalently and act as a single substance. So it acts as one particle. They have either a positive or a negative charge. Some common polyatomic ions is NH4 +1, which is the ammonium ion, OH negative, which is the hydroxide ion, NO3 -1, which is the nitrate ion, and SO4 -2, which is the sulfate ion. There's a lot more of these, and you're not going to have to memorize them because they are on the back of your periodic table. So now, if we want to predict some ionic charges, if you recall, we remember that group 1, all of our group 1 ions have one valence electron. So our group 1 elements are going to want to lose that one valence electron, forming positive 1 ions. Our group 2 elements they have 2 valence electrons, and they're still metals. They're the alkaline earth metals. So these are going to want to lose both of the electrons, resulting to form positive 2 ions. So we would see beryllium positive 2, magnesium positive 2, calcium, strontium, and barium all having those positive 2 ions. Group 3, or group 13, group 3A, are going to lose 3 electrons for the most part, resulting in positive 3 ions. Now, group 4A or group 14, this is going to depend. They have 4 valence electrons, so it's either going to, it can just as easily gain 4 or lose 4. Now, a lot of times what happens is this is going to depend on whether or not it's a metal or a nonmetal. Most often, a lot of group 14, especially in our period 2, 3, and 4, will often bond covalently. Now, our group 5A or group 15 elements have 5 valence electrons. So they have 5 valence electrons. So, and they're nonmetals. This means that they're going to want to gain electrons, and they're going to want to gain 3 electrons. They're going to form negative 3 ions. So we have N3-, which is the nitride ion, P3-, which is the phosphide, and As3-, which is the arsenide. Notice we're taking the root of each of these. We're taking the root of nitrogen, phosphorus, and arsenic, and adding that suffix IDE. Our group 6A or 16 elements, the oxygen family, remember these have 6 valence electrons, and they're nonmetal, so they're going to want to gain 2, resulting in O2-, S2-, and Se2-. Keeping the base or the root, we have oxygen becomes oxide, sulfur becomes sulfide, and selenium becomes seleniide. Our group 17 or group 7A elements, our halogens, have 7 valence electrons. They want to gain 1, and these are all going to then result in a negative 1 ion. So we have F-1, Cl-1, Br-1, and I-1. So fluorine becomes fluoride, chlorine becomes chloride, bromine, bromide, and iodine, iodide. Our final family, the group 18, the group 8A, the noble gas family, are stable. So our noble gases are not going to form any ions. They already have their 8 valence electrons. And then if you recall our transition metals, our transition metals can form multiple ions.